In this pre-calculus algebra video, we'll look at rational functions and their graphs. At the end of this video, you should be able to graph a rational function, and to do that, you'll need to be able to do a number of steps to get there. There are a list of several steps that we follow to graph a rational function, and what we'll do in this video is walk through each of those pieces one at a time so that we can build up to that goal of being able to graph a rational function. Another thing we'll be able to do at the end of this video is solve a problem such as this, average cost. You might be familiar with a cost function. The cost function is a function that describes how much it would cost to produce X units of a product. And the cost function is the sum of the fixed cost. So in this case, $500,000 is the fixed cost, and it's the sum of that fixed cost and the variable cost. So this means that it might cost $400 to build each unit, but then there's a fixed $500,000. You might think of it like this. You pay $500,000 for a factory, and that's the fixed cost. It doesn't matter how much you produce or don't produce, you've paid $500,000. And then the materials and labor for each item might be $400 a piece. So then if you made one item, it would cost $500,000 plus $400. If you made two items, it'd be $500,000 plus $800, and so on. But the cost increases by $400 for each additional unit. What we might want to be able to calculate is the, the C bar of X, the average cost of each item. So we would use the C bar of X, which is going to be a rational equation or function. And by the end of this unit, you'll be able to solve some application problems about the average cost. So let's get started with the domain first. Do you remember that the domain of a rational function, so a rational function is something that looks like this, where we have variables in the denominator. And the domain is that we have to restrict the domain so that there's no zero in the bottom, in the denominator. A zero in the numerator is okay, but we can't have a zero in the denominator. So to find the restriction on the domain, we would set x squared minus 49, the denominator, equal to 0, and solve. We're going to solve this by factoring. Do you see that difference of squares? So it factors pretty easily. And then once we factored it, we set each factor to 0. So x plus 7 is 0, giving us x equal to the opposite of 7, or x minus 7 is 0, giving us x equal to positive 7. So the domain of this function would be the set of all x's such that x is not 7 or negative 7. In interval notation, we'd say we can take all the x's from negative infinity up to negative 7, or negative 7 to 7, or 7 to infinity. So what we're doing for interval notation is making a list of everything that is included, and what we've done here is we've excluded negative 7 and excluded 7. This next example is quite different, because if we look at the denominator, the x squared plus 49, if we set that x squared plus 49 equal to 0, do you remember that that x squared plus 49 is the sum of two squares? There's no GCF. We can't factor this. Or if we tried the square root principle to solve this, we'd have x squared equals negative 49, and if we did the square root of both sides, we do x equals plus or minus the square root of negative 49. So what we're getting here is imaginary numbers. X is 7i, or the opposite of 7i. When we set this denominator equal to 0, we don't get any real numbers. So what does that tell us? It tells us that there's no restrictions on the domain. If there are no restrictions on the domain, then what we say that is that the domain is the set of all real numbers. You can write that with the symbol. This means the set of all real numbers. Or we could say the domain in interval notation is negative infinity up to infinity. Let's look at another example. This notation is maybe a new notation for you, and it's important notation to get used to, especially because this is a pre-calculus class. When we do some calculus topics in the future, you'll see this type of notation even more often. The way we'd read this is x approaches a from the right. So this little plus mean, it looks like an exponent. It means from the right. Or x approaches a from the left. We could also say that x approaches infinity, or x approaches negative infinity. And when we look at this example 2, true or false, if f of x approaches 0 as x approaches infinity, so as x is getting bigger, x is going this way, getting further and further to the right, we have f of x, y is getting closer to 0, so it might look like this. Notice that this line that I've sketched in is never going to touch the x-axis, the y equals 0 line. It gets closer and closer, but it doesn't ever touch it. Is that the same as the graph of f approaches the x-axis to the right? And I would say yes. That is what this notation is telling us. Let's look at another example. If we wanted to find vertical asymptotes. Vertical asymptotes occur when the denominator of a rational function, when that denominator equals 0. Now, one caveat here is that we do have to reduce it first. So my first instinct might be to say that there's vertical asymptotes when x equals 0, or when x plus 4 equals 0, which is when x equals negative 4. But that's not quite accurate for vertical asymptotes, because do you see that I could reduce this x over x? If I reduce x over x, because x divided by x is 1, then I could rule out this asymptote. However, it is something important. Here's what we can say about this. The vertical asymptote for this rational function is going to be at x equals negative 4. If I had a xy graph axis, when x equals negative 4, I'd have an asymptote. An asymptote, you can see the picture over here to the right of what an asymptote looks like. The graph approaches it but never touches it. So the graph of our function is going to approach this black line but never touch the black line. X equals 0 is not an asymptote. However, there will be a hole in the graph when x equals 0. So for example, if the graph of this thing went like this, what I'd have here is that when x equals 0, the graph stops. It has a break in it. And that's what we do with this x equals 0. The other value that made the denominator 0 before we reduced it. When we look at the second example, the vertical asymptotes, when we have f of x, or r of x equals x over x squared plus 4, this x squared plus 4, do you recognize it already? There we have again a sum of squares, and when we set this equal to 0, there's no real solution. There's only imaginary solutions because the x squared plus 4 doesn't factor, or if I did the square root property, so I'm going to subtract 4 from both sides and then do the square root of both sides, so that x equals, the square root of 4 is 2, so 2i, or the opposite of that would be negative 2i. But those are imaginary. We don't get an asymptote for those values that are imaginary. It is important. One important step of solving the problem of graphing a rational function is that you need to be able to find the vertical asymptotes and also find the holes in the graph. The next thing you'll need is to be able to find a horizontal asymptote. The horizontal asymptote is a line y equals b, and the line y equals b is a horizontal asymptote of the graph of the function if f of x approaches b as x increases or decreases. So it's approaching it, but notice over here, this last example, it is possible to cross, it's possible for the graph of a function to cross a horizontal asymptote. Now a vertical asymptote is different. You cannot even cross the vertical asymptote, but the horizontal asymptote, it is okay to cross. You will sometimes have a graph that crosses that. There's a bit of a long thing to memorize here. If you want to approach finding horizontal asymptotes by memorizing, I would say it's not going to be really easy. There's this long list of possibilities. Locating a horizontal asymptote, we've got if the degree of the numerator is smaller than the degree of the denominator, then we get y equals 0. If the degree is equal, we get the fraction that comes from dividing the two. So the coefficient of x divided by the coefficient of x. And then if the degree of the numerator is bigger than the degree of the denominator, then we don't have a horizontal asymptote. What we would have instead is a slant asymptote. I've always thought that this was really far too complicated. And so here's what I'm going to do. Let me erase that x first. I'm just going to delete this and say, let's not worry about memorizing that. Here's the one thing we can do to replace that. Here's the one thing we do. Divide this. Divide the top, but divided by the bottom. Divide top by the bottom. Long division. Looks like this. Negative 2x plus 1 divided by 3x plus 5. So we're doing negative 2x divided by 3x. It's negative 2/3. And there's our asymptote. What we would do is fill in the y equals, and there's our asymptote. It's the top, the numerator, divided by the bottom, the denominator. So in other words, to find horizontal or slant asymptotes, you just use long division, and that works every single time. We could see that work for this example that they did this long way, having memorized that list of steps. If we did this 9x squared top divided by 3x squared plus 1, that's the bottom, we would do 9x squared divided by 3x squared is equal to 3. X squared divides x squared. 3 goes into 9 3 times. So we'd have 3, and that's it. That's all we have to do. Y equals 3, would be the asymptote over here, and there they have it. But they found it having used that long list of 3 different cases. Let's try it again. If we do 12x top divided by bottom, 3x squared plus 1, do you see, oh wait, that 12x, the degree is too small. I don't get I don't get a linear result or I don't get a constant or a line, neither one's, because if I were to reduce this, we'd have 4 over x, because x over x squared, we'd be left with an x in the denominator. 3 goes into 3 once, 3 goes into 12 4 times. X goes into x once, x goes into x squared, x times. So we'd be left with 4 over x. So what that means, what we're going to do for that type of example is we'll say that the horizontal asymptote is y equals 0. How many times does 3x squared go into 12x? 0 times, because that 12x was too small. So we'd say 0. And the asymptote is y equals 0. So you see, you could use that divide, the numerator divided by the denominator, every time. Here's our next example, and here's where it all comes together. And there are 2 examples I'd like to work through, but I'm going to stop the video now to give you a chance to think through the other examples we've done. The next step is going to be graphing these rational equations, and I'm going to do an example. I'll do 3 different graphing examples and an application problem in the next video.